All right, everybody. So for today, we are going to finish notes 1.7. Now, we already talked about the transformation of absolute values, and that's where we move things up, down. And remember, the biggest thing was the a value, the h, and the k. So today, we want to talk about how you can do that with every single parent function you can think of. So a parent function is basically the simplest form. It is the simplest form of an equation. And what that means is it has no extra numbers floating around. So that's why when you look at all of these equations that are written out here, all of them, see, yes, I understand that has a number, but look at this. No number in front, no number behind it. This has no adding or subtracting, multiplying. These are all examples of parent functions. They have no extra numbers. Now, one of the things that you're going to be able to do for today is figure out, okay, well, what family do these equations or functions belong to? So when we're looking here at our family of equations, these are all the ones that we learned in Algebra 1. So there's the absolute value that we practiced the other day, but let's take them one at a time. So first things first, we have the constant function. Now remember, when they say something is constant, it means it never changes. And so that's why when you look at the equation, f of x is equal to 1, don't forget f of x is the same as saying y is equal to 1. And so if you look at the equation of the graph here, y is equal to 1, that means the y value is always the same. It never changes for these. So again, that's the idea of a constant function. But the other thing you have to notice about it, and this is how we recognize it, we recognize a constant function because it has no x. Look at that, it says y equals. So it has no x. And we've worked with this type of line before. In fact, we have a special name for this kind of line. We call it a horizontal line. It just goes side to side. The y value never changes. Now, be careful. One of the mistakes that people tend to make with a constant function is they think if it says x equals a number, they think that's constant. But no, remember, it literally has to have no x in it. All right, so now the next function we have that you learned in Algebra 1 is a linear function. We've been drawing these as well. So we have f of x is equal to x. Again, this is the most basic equation you can get. We're going to call it y is equal to x. So notice we do have an x, we do have a y this time. But here's what makes a linear function so special and makes it stand out from everybody else. See, a linear function, you recognize it because it has a power of 1. So there's an invisible power right there, but that's how we tell these apart. By looking at it carefully, this thing has a power of 1. All right, and so looking at the equation, of course, we can have lines. We already know that increase, decrease. And if you're thinking, yeah, but mister, isn't that a line too? It is. But this is a very special case, very special situation. Now, beyond that one, here's the one that we learned just the other day, the absolute value. The absolute value of x obviously is very recognizable because it actually has those bars written right next to it. So it says y is equal to, here come the bars, the absolute value of x. And just remember, the absolute value of x is always positive. So when you look at your graph, that's why the graph never dips under the x-axis. And so when we were graphing it the other day, even though we were throwing negative numbers in there, they were still turning out positive because that's what an absolute value does. But again, we'd also like to give this one a little name. We call it the v function. And just by looking at the picture, well, I think you understand why we call it the v function. And so we were graphing these the other day, and hopefully you get that practice and get to finish that work today. And then, of course, in Algebra 1, we get to this very last one, the quadratic. Again, the quadratic takes up almost the entire second semester of Algebra 1. The quadratic, we do know it has a special name for a graph like this. So here's the equation. F of x is equal to x squared. Don't forget, you could just say y equals x squared. But what makes this thing stand out? Remember, a power of 1 means you're dealing with a linear function, a line. So I should be able to look at an equation and go, hey, that's got a power of 2. Well, that's what makes it quadratic. The fact that it has a power of 2. And now we do have a special name for this graph, of course. If you think back to your Algebra 1 days, we call this a parabola. So there we go. Now, the other big thing here is domain and range. Now, remember we did talk about domain and range the other day as well. Domain, we said, are the x's. The range are the y's. So here's my range here. And every graph is different, but you should notice something in common. Remember, when we say domain, we always talk about going left forever, right forever. So when I look at this graph, it does go to the left forever, and it does go to the right forever. So that's why the domain says all real numbers. When I look at this graph, does the graph go to the left forever? Absolutely. Remember, it's slanted. When it's slanted, it means that it's actually heading down and to the left forever. If not, it wouldn't be slanted. So it does go to the left forever. When I look at this side, it does go to the right forever also. So notice, that's why we say all real numbers. For domain and range, you ask yourself that question. Does it go left forever, right forever? Look at the absolute value. When we're looking at the absolute value here, it goes left forever and up. Yes, I get that. And it goes to the right forever. So again, notice the pattern here. Every equation, even this one, look at that. Left forever, right forever. It doesn't shoot straight up. It's actually slanted, so it is moving to the left and to the right. But that's why all of these have an answer of all real numbers. That's why when you did this homework assignment, we said, that's going to be the easiest question on your homework. Because when they ask you for domain, the only graphs that you've learned in Algebra 1, the domain is all real numbers. Now, the range is the one that obviously changes depending on the graph. For instance, here, the range are my y's. So then this is where I ask the question, do I go down forever and up forever? Well, this doesn't head down. This one only goes side to side. It doesn't go up or down. In fact, the only y value you're allowed to pick, that's why it's called a constant, is y equals 1. So that's why my range, that's the only number that gets used. Look at that. This point, this point, this point, no matter what point we think of, it's always going to be a 1. Now here, if I ask you, well, does it go down forever? Absolutely. And over here, well, does it go up forever? Yeah, it does. So that's why if you notice, the range is also all real numbers, but we're asking about up and down, not left and right. And then there's the absolute value. We practiced this one the other day. It does go up forever, but it doesn't go down forever. So when you say, oh, it doesn't do that, we write the y right away. It went up forever, so that's why it's greater. And then the lowest, very low y value that we get to, right there, y equals 0 is the lowest y we get to, and then the graph only exists up here, and this is what we mean by range, so that's why it goes above the 0. And of course, when you look at the quadratic is doing the same. It goes up forever, not down, so that's why they said y is greater, because it goes up forever, and the lowest point, again, is 0. See, our smallest y value, well, these pens are out. The smallest y value is 0, but then the graph goes up and up forever. So when we're talking about range, remember, we have to ask these questions. So now, the next task that we have to do is probably the easiest one. Okay? All they're going to do is, they're going to show me an equation, and I have to make the decision. What do I call it? What family does it belong to? Well, remember the tricks. A constant is y equals, there's no x. A linear, the biggest power you should have is 1. An absolute value, well, clearly you have to see those bars. And a quadratic, well, the biggest power you see has to be a 2. So, here we go. First example, it says, determine if the function is constant, linear, quadratic, or an absolute value. In fact, let me try to get it all in the picture here so we can see what we wrote. All right, so when I'm looking at this first one, we see here, it says y is equal to negative 4x squared plus 3. Now, if you know the answer, great, write it down. But you see what stands out? That's what's calling the shots. And so looking at that value, we automatically know this is a quadratic. So we have a quadratic equation. Because of that power 2, it comes down to that. Now, looking at number 2, we have a y value, of course. We do have an x, so it can't be constant. These are parentheses, not bars, so it's not absolute. It doesn't have a power of 2 anywhere. But what I do notice is that that little x right there basically has a power of 1. Even on the outside, there's a power of 1. So it's that. That's what's calling the shots here. No, they're not always going to look like this. Keep in mind, they're going to add numbers and do all these crazy things to it. But this would be a linear function. All right, so then we look here. It says x is equal to 4. Now, of course, there's no power of 2. There's no absolute. There's no power of 1. Well, actually, there is. It says x. And if you're thinking, oh, that's a constant, look, it's just a number. Be careful. A constant needs to say y equals. It can't have an x in it. Well, this one doesn't say y equals. It says x equals. This is what we call a vertical line, and vertical lines are not functions. So remember, we do have the option of saying neither. So in this case, this is not constant. We would have to say it's neither. So again, that's the one you got to watch out for. Yes, it only equals a number, but because it only equals a number, doesn't make it constant. It has to say y equals. And then finally, we look at this one. Now, you might know this symbol from back in your Algebra 1 days. We call that a square root. So what we could say is, oh, this function's a square root, and we'd be right. But notice, technically, that's not one of the options. So no, it's not constant. You might say it's got a power of 1. No, it's got a square root, so it's not linear. No power of 2. There's no absolute value. So once again, we're going to have to say neither. All right. So now, you're going to do the same thing. Okay? You're going to do the U-tries here. I do want to show you one of these bottom ones. So here, you're going to do exactly what I did earlier. You're just going to name what family it belongs to. Then when we get to this one, it says, well, give me an example of what an absolute value equation would look like. So here, everybody should have a different answer, but we'll do one together at least. If they want an absolute value, well, then I have to have this. So y equals, first of all, I'm going to give it the bars. And if it's an absolute value function, I'm going to put the x in there. And now I can pretty much do anything. Look, I could put a number in front. I could put a number on the inside. We can even put a number on the outside. Remember, this is what we were working on the other day. So for these 3 problems, just write me any equation as long as it fits the rule for quadratic linear constant. All right, so we're going to pause the video for a moment. That way you can try these out. So let's pause the video now. All right, now that you've gotten the opportunity to try these problems out, let's check your answers really quick. So you see this one says y equals 3. Okay, that's good. This one does have a y and a number, so hopefully you wrote constant. That's a true constant right there. When I look at this one, yeah, it looks very different, but this is what stands out. It has a power 2, and yeah, if there's an x in there, that x is going to get that power of 2 eventually. So that right there, hopefully you called it a quadratic. When I look at the next one, number 3, look at that. There's no absolute value, no power of 2. It has an x, so it can't be constant, but it does have a power of 1. It's invisible, so that's what makes it linear. And finally, of course, obvious, look at that. It's got the bars, so because of the bars, we call this an absolute value. All right. Now, these, all of you should have different answers for these. Just remember, if you said it's a quadratic, you had to make sure the x has a power of 2. If it's linear, just make sure your x has a power of 1. And if it's constant, it just has to say y equals, and then you can pretty much pick any random number you want. Look, -6 if we wanted to. But the idea is we have to understand that back in Algebra 1, we learned all these basic graphs, and we're still going to need them. All right, which leaves us with one last page for today because we just needed to finish the notes. We don't want to rush it. Right here. So page 21. So we have 4 problems that we're going to try out, and then you're going to try out the last 2 on at the bottom on your own. So what we're going to do right now is we're going to do the exact same thing. I want to know what family it belongs to. Which constant, right? Linear, quadratic, absolute, or maybe it's neither. But what I want you to be able to do is I want you to be able to look at the numbers and just be able to name it by looking there. There is a graph in case you want to draw it, and that will help you. Remember, you can always draw using tables. So let's check it out. The thing that stands out to me right away is look at that y value. That y value is the same the entire time. It's not changing. Well, then if this thing there's no change, then that means, look, I know that we can skip count here. Look, we'll say that's 5, 10, 15. And then we'll say that's 9 right there. 5, 9, 5, 9, 10, 9, 15, 9. So if you notice, this is just a constant equation. So that's why you can always graph it. It'll help you figure out what kind of equation you have. Or just look here. The fact that none of the numbers changed, that's what tells us that this is a constant function. And again, it says when looking at the table, I can tell because the y values do not change. Simple as that. All right, so let's look at number 2 here. Now, when we're looking at number 2, here we go. We see the x's. Now, notice something about the x's. I didn't even bring them up last time because I noticed that these were exactly the same. See the x's? When we look at patterns, and that's what math is all about, looking at patterns, all of these numbers are just going up by 1. So the x doesn't really help me. It's the y values that are going to call the shots here. Remember, the range is what kind of tells us what this equation is going to be. So let's look at these numbers. All right, so think about patterns. We want to know how the numbers are changing. So the first question is, how do you go from a 7 to a 9? And if you're thinking, well, I have to add 2, you're right. How do I go from a 9 to an 11? Well, yeah, you got to add 2 again. 11 to 13. What do? We have to add 2. All right, and then we keep it going. 13 to 15, we add 2. 15 to 17, we add 2. So now notice, the numbers did change. So it can't be constant. Constant is out. What we do notice is that the change is very consistent. See, these numbers didn't change. It keeps going up by the same amount over and over and over and over. So when this happens, when it's the same number over and over, when that's the pattern, we call this a linear function. Well, we're just going to say linear right there. And again, if you didn't see it, well then look, 2, 7, 2, 1, 2, 3, 4, 5, 6, 7. So that barely fits there. 3, 9 would be up there. The next one up there. So see, it's very linear, even though the graph didn't really help me much. But again, we want to look at patterns. Math is all about patterns. All right, 2 more to go here. Let's try them out. Oh, wait, we didn't give a reason. The function is linear. When looking at the table, I can tell because the y values change. So they do change. Look, it's not the same number. The y values change at a constant rate. This is what we mean. And I might want to say consistent because I don't want you to confuse it with this, but it changes with a consistent rate. Okay? But you can always draw it if you can't tell what it is. All right, and then we get this one. So number 3 and number 4. Last ones before you do the you tries. All right, so again, when I look at my x's, how do I go from a -3 to a -2? I'm adding 1. -2 to -1. I'm adding 1, adding 1. So you see, this doesn't help me. That's why I mentioned earlier. The one that's going to call the shots is the y value. That's the one that's going to call the shots. So let's see what's happening with the y's this time. Now I notice the numbers are getting smaller. So I'm going to try subtraction. So 12 minus 5 is 7. Okay, I'm going to try it again. 7 minus 5. Okay, so it's not a minus 5. So notice, the numbers are all different. So constant is out, right? It's not one of these. That one doesn't make sense. This one doesn't drop by 5, which means linear is now out. They have to change by the same number. So then, how do I go from a 7 to a 4? Well, I subtract a 3. How do I go from a 4 to a 3? Well, I subtract a 1. Again, it's all about patterns here. How do I go from a 3 to a 4? Well, notice, now they're going up by 1. 4 to a 7. Now they're going up by 3. And then this one goes up by 5. So look at that pattern. It does have a pattern. Look, the numbers ended up repeating themselves eventually, but they were going in opposite directions. But the y values did change. but they didn't change by the same rate, and they did change in opposite directions. All right, before we answer this one, let's go look at the pattern over here. Remember, I'm really down to a quadratic and an absolute value. All right, so let me look at this one. When I look at my x's, clearly they're going up by 1. So that's easy enough. They're just going up by 1. So again, the x's, they don't really help us. Not for this. If I want to figure out what kind of function it is, it's the y's that call the shots. So now let's look. I go from a 2 to a 1. Well, the only way to do that is to subtract the 1. From a 1 to a 0, I'm subtracting a 1 from it. But then to go from 0 to 1, I'm going up by 1. From a 1 to a 2, I'm going up by 1. So notice, the y's are changing. But they're changing by the same value, right? 1, 1, 1, 1, but in opposite directions. So the question becomes, all right, well, see this one right here looks a lot like this one, where it follows the same kind of number over and over and over, but in opposite directions. That is why this one right here is the absolute, I was going to say ABS, value. Because when looking at the table, I can tell because the y values change by the same value in opposite direction. Remember, one's adding, one's subtracting, so they go in opposite direction. But all I have to do was just look at my numbers. Now I could also draw it, right? Like 0, 2, 1, 1, 2, 0, 1, 3, 1, sorry, 4, 2. Look at that. There's the V. There's that V shape. So then what that means is, well, we were down to one more. So obviously this one has to be the quadratic. So look at how the quadratic really changes, right? The quadratic changes, the numbers are all different, but even these numbers are different, but they go in opposite direction. So the y values change by different values in opposite direction. Now I'm going to bring back a little fact, again, opposite direction. Now I'm going to bring back a fact from your Algebra 1 days. Now in Algebra 1, we talk about this like once. We mention this one time and then we just kind of move away from it. Remember, a quadratic has a power of 2. So whenever you get some weird numbers that don't fit this pattern, right, they're not the same, it doesn't fit this one, it doesn't fit this one, and you think, oh, it's quadratic then. Well, there's a way of checking actually, and that's to find a second pattern. So if you look here, here's my second pattern. -5 to -3, that's actually me adding 2. How do I go from -3 to -1? Well, I add 2. -1 to 1, I add a 2. 1 to 3, we add a 2. So notice, this pattern is consistent. And because this pattern is consistent, but notice, it took 2, hello, power of 2, right? This is how we can tell. So if it ever throws you off, because you're not quite sure if it's quadratic, you can always do a second pattern to run a test. All right, everybody, with that said, you should be trying out these last 2 problems here on the U-tries. We'll check the results, and if it's all good, then get started on today's homework. It is a BIM. Remember, you already have the pink packet that has the homework in it. It's the very last 2 pages, I believe, homework 1.8. Very important homework for one reason. It has some of the test questions already. It's your first test review. So homework 1.8 is definitely not one that you want to skip. So make sure you're trying it in class. Get some help with finishing it up because you want to get the practice for next week's test. With that said, have a wonderful weekend, everybody.